Vijay. Thank you very much.
Great. Thank you very much. Thanks very much for this invitation. And as somebody said, thanks to the organizers for doing this at a very strange global time. Some of you may be noticing that seem to be sitting in a car. That is because it is a really weird time. We had a huge thunderstorm an hour ago, and all the trees came down and the power's out everywhere. So I have driven to the parking lot of a McDonald's near where we live, where they have free Wi-Fi. And I'm sitting in the car and giving this talk. Anyway, so first time in my life, perhaps the last time in my life I do this. Okay, so anyway, in view of that and view of the limited power, therefore, my laptop, you should please feel free to ask questions, but I will feel, during my talk, that would be better that way, but I will feel free to defer the question to later if I feel I need to move along in order to be able to get through the talk. So I'd like to give a talk today on the quantum complexity of time evolution. This is basically talking about work that I did with Matt DeCross. I was a student at Penn. Arjun Kar, who just graduated and is moving to the group of Markman Ramsdong in UBC, and Onkar Parikar, who is currently in the group at Stanford. I think Arjun and Onkar are both on the call. So if my power gives out by the end and I can't answer questions, I'm sure that they'll be able to answer the questions better than me. Okay, so right, so this talk is about complexity, and in many branches of physics, we talk about complex systems. And complex systems typically means we're talking about systems with many internal components, many body interactions, multi-party correlations, and emergent behaviors. There's a lot of interest in these kind of complex systems in biophysics and strongly interacting materials, social networks. And of course, for us, a primary interest in our field, at least in the string theory part of the community listening to this conference, concerns black holes and their microstates, which are evidently appear to be very complex systems, and in thermodynamic systems in general, and also in ADS-CFT, where there's some sense that the ADS, the emergent space-time that's dual to the CFT, somehow emerges from the complex dynamics of a large NCFT. So in all of these words, when we say these complex systems, I think one of the key puzzles or interesting things is how is the term complexity to be defined, and in what way is the notion of complexity related or not to conventional things that we care about in physics, conventional objects and things that we've computed before. And just as a very simple example, can complexity, for example, be used as an order parameter to separate perhaps integrable and chaotic theories, as an example that you could ask. Now, we're less used to thinking about complexity in physics, so we might as well take some tips from computer science and information theory, where there are, in fact, various relevant notions of complexity. And the reason we will be interested in those notions is because there's a conjecture coming out of the physics of black holes, due essentially to Susskind, that maximally chaotic systems will have complexity, whatever complexity precisely means, that grows linearly in time for an exponentially long time. So if we knew what we wanted to define complexity to be, we could try to prove that. But then we first need to define the term. So that's really the underpinnings of the talk today. Let me ask, can people see my screen and people hear my voice clearly?
Yep.
Yes.
Excellent. So then let me go to the next slide. How do I go to the next slide? Oh, there we go. Okay, so in computer science and in information theory, there are various notions of complexity. And in the end, most of these notions have something to do with how a big thing or complex thing is made of little things or simple things, and how many simple things you need to make the complex thing. So for example, going back to ancient times, there is the notion of Domogarov complexity, in which the complexity of an object is understood to be the length of the shortest computer program required to produce it. So this is kind of the Ur notion of complexity, right? The primordial notion of complexity. So for example, a random number sequence is complicated because there's no algorithm. You just have to write down the numbers, and that's a lot of numbers you need to write down for a very long sequence. Whereas pi or √3, pi looks very complicated as a number sequence, but it's very simple because there's a short program you can use to produce the digits of pi. So this is a kind of algorithmic complexity, procedural complexity in how you generate something. So in information theory, there are other notions like stochastic complexity due to Rissanen, in which the idea is that the complexity of a message is the size of the smallest code you can use to compress it. So you imagine a code book consisting of some number of alphabet letters, and you take some long message and you wish to compress it in the shortest sequence of code, letters that you could use, and you use that to define the complexity of messages. So clearly that's related to this notion of Kolmogorov complexity in one way or the other. So in computer science, very often, a related notion of complexity is used in which you say that the complexity of a class of problems of size n is some f of n, which is the size of the smallest program you need to calculate the answer. Clearly, this is related, for example, to the notion of Kolmogorov complexity. And if you wanted the computation to be carried out by a circuit, for example, this thing down here, I hope you can see my cursor. Imagine that you have a bunch of input bits, 0, 1, 0, 1, etc., n of them. You imagine putting together a circuit built out of some repertoire of elementary, quote, simple gates to build a computation, and then you declare that the complexity of the whole thing is the, let's say, the depth. You could choose different things. You could choose the depth of the circuit. You could choose the number of gates required to do the computation, and you define the complexity of the computation or the computational class in those terms. Now, clearly in all of these definitions, the complexity depends to some degree on what you pick as your repertoire of simple elements. So because of this, very often complexity is spoken of in terms of a scaling law as opposed to a precise number. You say as the problem size grows in n, there is some scaling with n which defines the complexity of the class. At least in computer science, it's that way. And in comparison, very often when we're talking about things like black hole physics, we actually want a number because we want to compare it to the volume or the action or something like that. And so that remains something that we need to think about in the field, about this difference in perspective of scaling laws versus sort of actual numbers for the complexity of a thing. So for our purposes, we're interested in the complexity of quantum mechanics considered as a computation. So how do we think about quantum mechanics as a computation? So let's consider some initial state here, you know, a bunch of qubits, for example. And then we have some final state at some later time, psi of t. And we imagine that we know that the time evolution operator, e to the minus ht, transports us from the initial state to the final state. Okay, so what would make such a time evolution simple or complex? So suppose you had an initial wave function that looked like this little Gaussian bump, and let's suppose it evolved after some time into some, you know, a couple of bumps spread out a bit. We might be tempted to say that this is a simple time evolution because you can imagine many simple operations acting on the initial state. You can imagine like building a quantum computer in a lab with lots of little lasers and what have you to manipulate this wave function into this wave function. That seems like something that would be relatively straightforward to do. By contrast, if you had a time evolution that took this little Gaussian lump into some very, very complicated, you know, bumpy wave function with lots of non-local entanglement, you might think that it'd be very difficult to to transport this wave function to this wave function using simple local operations. You need large local and global changes and substantial non-local correlation. So that would appear to be something that we would want to call a complex time evolution. Right? So we would somehow like a notion of complexity that reflects these kind of differences. So how can we construct such a measure? So one way of thinking about this is to think about the complexity of states. Namely, here's a state. This may be a simple state, whereas this kind of non-locally correlated state may be a complex state. But really, the interesting thing is not, can you make a complicated state? Because of course you can. You can build a very, very complicated thing, and this would be complicated over here on the right and less complicated on the left. But really, the interesting question is, does physical time evolution produce complicated things, right? So that's what we're really interested in. And in view of that, we might say that we're interested in the complexity of time evolution, right? So in the sense that we want to take the operator e to the minus iht that does transport in time and find an appropriate measure of the complexity of that time evolution operator. So how can we do this? Do here? Yeah, there we go. So how can we do this? Well, okay, so again, so what is time evolution? So suppose you have a Hilbert space of n over 2 qubits, then, well, time evolution is generated by unitary operator in this Hilbert space. So I have some operator that lives in SU 2 to the power n over 2. So as time passes, e to the minus iht traces out in this way a trajectory in the unitary group. So the unitary group, of course, for SU2, if you've got two of these things, is just S3. It's very simple. It's a sphere. And so you can imagine the trajectories on that very easily. But if you're talking about SUN, so many qubits, SUN is a complicated fiber bundle. And so, well, somehow the complexity of time evolution should be related to the complexity, in some appropriate sense, of these trajectories on this complicated fiber bundle called the Lie group SU2 to the power n over 2. Okay, so how do we think about that? Well, so if I go back to the cues from computer science and want to think about how complicated this trajectory is, you might think, well, one way of thinking about this is suppose you discretize this trajectory and break it up into many little pieces. The number of steps or the length of the curve is somehow a measure of how complicated or long, how many operations you need to perform to get from the initial, from the identity operator to U of t. So that you might think that would be a reasonable measure of complexity. So indeed, right? If you think in that language, you might suppose U of t is the current time evolution operator, and this initial dot here is the identity operator. So this is U of t at U of 0. Then you might think that it would be a good idea to define complexity of this time evolution as the length of the shortest path or geodesic on the unitary group between the initial point and the final point. So that maybe the time evolution operator follows this in a solid trajectory. And in fact, the geodesic goes this way. And then you might suppose that in some appropriate metric, the complexity of the unitary time evolution is the length of the geodesic. In other words, the smallest number of steps you need to take to get from the identity to this point, to the U of t, in some appropriate metric. So now this is an idea that has been suggested before, notably by Nielsen and Dowling. And these authors basically said that, showed, in fact, whoops, what's going on? Showed that the geodesic length, in this sense, on the unitary manifold in an appropriately constructed metric, is in fact equivalent to quantum circuit, polynomially equivalent to quantum circuit complexity. So in other words, what they were interested in as computer scientists is they actually want to know, how many gates does it take to perform some computation, and they showed that if you compute the geodesic lengths in this way, in the appropriate metric, the length you get is polynomially equivalent, namely up to some polynomial change in the basis for computation. It is equivalent to quantum circuit complexity. Now,
Vijay, can I ask a question?
Yes,
Sorry,
yep.
This is Rob.
Yeah, hi, Rob.
Hi, how are you doing? When you're writing this symbol, you're saying it's the complexity of the operator, but you really seem to have in mind that it's the operator acting on a particular state, no? I mean,
no.
No.
Because we're here thinking about this as the operator, let's say e to the minus IH2, and we're going to construct the geodesic from the identity to this operator, regardless of which state it's acting upon. So we don't have to, for example, assume we're acting on a thermal state or something like that.
No, I was more thinking that if I act on an energy eigenstate, that doesn't seem very complicated at all. And I wouldn't get an interesting geodesic, but I guess
that's so
your definition is I act on the identity and see where it goes, or you have in mind a particular start.
U of 0 is the identity.
Yeah.
E minus IH times 0 is the identity.
Oh, I see. Yeah. Okay.
Yeah. So we're going to think exactly in terms of the operator, while understanding that you might be able to construct special states on which the time evolution is kind of trivial. Yeah. And energy eigenstates are clearly such states. So, but again, when you think about things like computational complexity, if you say that, traveling salesman is a hard problem, there can be instances of traveling salesmen that are trivial. So for example, if you've got cities in a line and you have to get from the beginning to the end, it's trivial and it's easy to solve. So it isn't true that in a complex complexity class or the difficult complexity class, that all problems are difficult. It's simply a statement that there exist difficult problems.
Could I ask a quick question? This is Norm Margolis.
Hi.
Hi. You have a problem in defining complexity. I mean, suppose I wanted the 10 to the 100th digit of pi or something in a computation. You know, in binary digit, it's either a 0 or a 1. I can make a unitary operator that produces either a 0 or a 1 in one step. So how do you make, you know, if you don't have to have the computation in between, you just have to have the right answer. How do you define complexity to be high for a hard calculation?
I'm not sure I've understood the question really.
You know, I mean,
here is to find the 101th digit of pi, right? So, or whatever, the billionth digit of pi. And so if you don't have any input, you need to have some way of computing that digit. The fact that the answer is not bit doesn't make the problem easy.
No, but how do you capture the idea that you have to do the computation if you're just making your complexity depend on getting the answer?
I'm not sure we're doing
once
that.
you've done the computation, you know the answer. You could just replace the computation with a lookup table that gives you the answer. How do you capture the idea?
Then you'd have a very big lookup table, right?
That's true.
Right. So you know, there's some issue here about, you know, you can trade space and time and the number of gates and stuff like that.
You're saying it has to be something that can that the computation does not depend on a particular input. It has to depend on that there's some large number of possible inputs, and therefore the computation has to actually happen. That's how you're making sure your definition actually.
Right. So complexity isn't defined by saying that here I have an instance, let's say again, of the traveling salesman problem.
Yeah.
And I want to find the solution to that instance, right? Because as you say, well, for that instance, you could write down the answer and just keep it in memory and store and spit it back out. I think that's what you were maybe perhaps alluding to.
Exactly.
Right? But that is not the problem, right? That is in fact an easy thing to do. That's one bit that you need to store. You don't even have to, the next time you ask, you don't even have to do the computation. You just spit out the bit. Fine, no problem. Right? But that's not the question. The question is, you have to define it in terms of a problem class, right? There's a bunch of possible initial conditions, and you need to compute the possible final conditions. And in easy problems, for any initial condition, you can compute the answer easily. For hard problems, there exist instances which are very hard.
Okay.
Right. And there are some, you know, and there are some classes for which, you know, the typical instance may be easy, but some are very hard. And then there are other problems where even getting approximate answers is hard in most cases. You know, so there's problems, there's complexity classes that are varying difficulty in this sense.
Okay.
Okay. So,
thank you.
All right. So, so the key question then is, so I wanted to say that in physics, it seems actually very natural to use the geodesic length on the unitary manifold, because of course, in computer science, these geodesics are kind of approximating at the discrete complexity of a finite time computation of a discrete computation. But you know, in physics, you know, everything happens in continuous time. So it seems very natural. You actually want to think about these trajectories on the unitary group and how they're structured. So what is the right metric is the question. And again, here we could take a cue from the work of Nielsen. And let's think about these trajectories. Okay, so suppose you want to think infinitesimally about tangents on this trajectory. So you can construct a tangent by taking the generators of SUN, multiplying with some coefficients, and then there's some operator, which is VITI written here, which will be, you know, some operator sitting on the tangent. Now we might say that we need a definition of simple and complex, and you could think of different kinds of things. So in a quantum mechanical theory, you might say that a simple operator is k local, by which I mean acts on less than k elements. And you might say that a complex operator is one that's not k local, so it acts on more than k elements. And of course, if you also had something like a field theory with space and so on and so forth floating around, you might wish to include in your definition of locality, you know, physical locality. It's not only k qubits, but they are nearby k qubits. So you could imagine various versions of this, and none of that has been very particularly well investigated, I would say, in our field, worth thinking about. Anyway, so it turns out to have this polynomial equivalence between computational complexity and, you know, the length of these geodesics. Nielsen found that you need to set up a metric on the group space, which is small in the k local directions. So in the local directions, it's sort of an order 1 metric. And large, by large, I mean of order e to the entropy, the log of the dimension of the Hilbert space in the complex directions. And so this kind of a metric tries to capture the idea that an operation is complex if you need basically correlated action on many elements to do it. So in effect, you need exponentially many simple actions in order to be able to do this computation. Okay, hold on 1 second. I'm having a problem with my screen. Okay, great. Great. Let me keep going. My screen keeps trying to shut itself down. I don't know why. Okay, here we go. All right, great. So in this language then, we want to think about the complexity as the length of the shortest geodesic path in this special metric, which is sort of exponentially big in the entropy in the complex directions and is small or order 1 in the simple directions. So because there's a finite possibility that I won't get to the end of the talk, my computer will die or something, I'm just going to tell you the punchline of what we find, and then I'm going to try to go quickly through how we find these results, and that will bring me to the end. Okay, so we are going to show 3 things in this language. The first thing we're going to show is that there is always a linear geodesic, by which I mean that suppose the Hamiltonian right here is a linear combination of simple generators. So we imagine some kind of local Hamiltonian. Then there is always on the unitary group manifold a linear geodesic that sort of essentially flows along the trajectory of the Hamiltonian. And this thing has a complexity that grows linearly in time. Okay, complexity in the sense of geodesic length on the unitary manifold that grows linearly in time. So that's the first statement. The second statement that you can show, you can prove, is that up to global obstructions, and we'll say more about that later, these are important and we will not be able to address them. So up to global obstructions, this linear growth in complexity will persist for a time exponential in the entropy, provided a certain condition is satisfied. So we call this condition the eigenstate complexity hypothesis, and it's this combination, so Rmn is the following thing. So in the numerator, we have a sum on all the easy or simple generators of the matrix elements of those generators squared between eigenstates m and n. And the denominator you have, this is normalized by sum on all generators, both simple and complex, of the matrix elements of all generators between the same energy eigenstates, let's say m and n squared. And the condition is you need this quantity, Rmn, to be equal to be suppressed exponentially by e to the minus twice the entropy of the system times a polynomial in the entropy of the system times some random numbers, right? So if this is true, it will be a fact that the minimal geodesic going between the identity and the time evolution operator has a length that grows linearly in time for an exponentially long time up to global obstructions, okay? So that's so this means that if this goes on for an exponentially long time, you wind up with an exponential complexity after an exponentially long time. So that's what this means. Okay. So
Vijay, a quick question. So is this condition sufficient or is it necessary?
It is sufficient. If
Thanks.
this is true, the implication is if this is true, then their complexity grows linearly for an exponentially long time. That's the implication is in that direction. Okay, we didn't show the other direction. Arjun and Onkar can chip in and correct me if I'm not saying correct things. Okay.
And in all this, you're assuming that the Hamiltonian is time independent, the one that generates your unitary? No. Okay.
I don't think that's actually necessary here. Though I don't think we actually come to think of it, we didn't actually study time-dependent Hamiltonians. Actually, so I said no because I don't think it will, but we actually studied time-independent Hamiltonians. So I'd have to think a little bit to make sure that the statement that I just made is precisely correct. Okay.
Another quick question.
Yeah.
You said S is an entropy?
Yes.
An entropy of what?
Okay, so let me try to see if I can get back to the previous page. I can't.
Sorry.
Hold on. Okay, it's entropy here means log of the dimension of the Hilbert space.
Great, thank you.
Perhaps I didn't say that. Okay, so just to show that this is not sort of a null condition that's completely useless, you can show that if you take a integrable version of the SYK-like theories, then they fail this criterion, and indeed complexity growth terminates very quickly. And if you take the SYK model, Sachdev, Kitaev, Ye Kitaev model for large n in a regime which is chaotic, then it satisfies this ECH hypothesis. And so you can show, so basically there are non-empty sets of theories, if you like, that do or do not satisfy this criterion. So in this talk, we will not have the time to show the numerical data supporting the last statement. So I will instead try to argue the rest of it.
Sorry.
Okay.
So Vijay, is this comment, sorry, so is this comment about SYK for large n, but still finite? So that's how you can see that it's like this exponential correction or something like this?
Yeah, that's a very good point, because actually proving this numerically involves, you need to show some, decaying exponential and so on. So we can't quite do that, right? So what we did instead is we checked a couple of large n's, or large here on a computer, n, n equals 10 is already large enough for our laptops, by the way.
Mm-hmm.
And showing that the order of magnitude of the terms is kind of what you'd expect.
Consistent. Okay, thank you.
So it's not more than that. We actually have a project going. There's a student, Kathy Lee, who's been working on a project of trying to understand that kind of thing better, nail that better for SYK, nail that a bit better for integrable and chaotic spin chains. That's very much still in progress. So I hope to report on that today, but I think it's going to have to wait.
Thank you. So
Okay.
I think I missed something. The alpha dot are labeling complicated generators.
Yes.
And how many of them are there?
There are vastly more of them.
I see. So for this to fail, this second term needs to be sort of 0 often, or very small often. If it's order 1, then you'll get an exponential suppression just by the number of terms
Let me talk a little bit about the intuition for what this is supposed to mean. Okay.
Thanks.
So what this is supposed to mean is that I'm having trouble with my okay. So what does this mean as a condition, right? So the basic argument, intuitively, what this condition appears to be saying is that local operations, the stuff in the numerator, cannot move you between energy eigenstates very easily, right? So that's what it's trying to say. So the numerator, right, basically can't compete with the denominator. So these things, will give you some generic value in the overlap, the denominator. And the numerator, it's not possible to go between m and n very quickly or very easily using simple operations. So that's what this is supposed to provide an intuition for. And before my power at home ran out, I was going to add some comments about it's vaguely similar to ETH, right? Because in ETH, remember, the condition is that for simple operators, and only for simple operators in complex microstates, in some complex states, the expectation value is the thermal thing plus something that's exponentially suppressed. There are some differences in this condition, where here you're talking about the simple operators here, but m and n are sort of all the eigenstates. Then you have, there's a square, there's an e to the minus 2s. There are some subtle differences between ETH and ECH, and that's also the precise relationship is not something that we fully understood yet either, and that's also something we're thinking about. Okay, so I'd just like to give you some sense of how these results arise. I think I have Hugo, could you correct me? I think I have about 15 minutes to go.
Yes, about 15 minutes.
Okay, good. Okay, great. So I will try to give you a flavor of how we do these, how we arrive at these results in those 15 minutes. So obviously that's a short time, so you will only get a flavor, not the details. So remember, our goal is to compute geodesics and their lengths on the SU2, on the SUN manifold. So the first thing we will demonstrate is that there is always a geodesic path along these simple directions from the identity to e to the minus I ht, whose length grows linearly t. So that's the first part that we need, right? That's the linear growth. So we'll show that first. So the way we get at that is you imagine a Hilbert space, right, of dimension n over 2, 2 to the n over 2. So this is like the SYK model with n fermions. Here are the n fermions, and here are the couplings. The SYK model, for those people who are familiar with it. And remember, the SYK model, these couplings are drawn randomly from a Gaussian with some variance. Okay, so that's, you can keep that, for those of you who know the SYK model, you can keep that example in mind. So now we have a unitary group on this Hilbert space. So that's SU 2 to the power n over 2. And the way we're going to think about this is, first of all, we need a basis to write down the tangent space. And so you can take, for example, the gamma matrices as a basis for the SU 2 to the n over 2. And that's like, for SYK people, that's like taking psi A, these fermions, as being the gamma matrices, as being related to the generators. So now we're going to construct the full generator, all the generators of SU 2 to the n over 2 in the following way. You can take products of gamma matrices, right, in particular order, and relabel these as the basis elements for the Lie group SU 2 to the n over 2. And so using this representation of the Lie group, you can write down the metric that we need. So again, you don't have to follow all the details of what I'm saying. I'm just trying to emphasize that a lot of the discussions about complexity, it's difficult. This is a difficult subject to do concretely. Say lots of things at a qualitative level. You can say beautiful things like people at Perimeter have done using free theories. It's very difficult to say things in general for interacting theories. But I'm trying to emphasize here that you can, in a very practical, nuts and bolts way, do these calculations. I've written down here generating a basis for the generators of SUN. And now, in terms of these bases, we're going to write down a metric in which we will compute the geodesic lengths and complexities. So in this basis, if you write down the commutators of two generators, you have the structure constants Fijl times TL on the right-hand side, and a conventional metric you often put in a Lie group is the Cartan killing form, which is constructed in this way on the right from the structure constants. So we are going to pick a metric that's related to the Cartan killing form, but modified in a particular way. So Gij, the metric we have on the group, is going to be the Cartan killing form times Ci plus Cj over 2, where Ci are going to be cost factors, where we take the Ci, the cost factors, to be order 1 for a k local index I. So if you have a generator of k local, a k local generator, then the Ci is going to be 1. And if you have the index j or I is not k local, we will take the cost factor to be 1 plus mu, where mu is some exponential in the entropy. This is, again, we're taking this because, that's the kind of thing that gives you the correspondence with computational complexity theory. Then with this definition of the metric on the group, if you give me tangents x and y at the group element u, then, you pull that back to the identity by taking x u inverse, y u inverse, and then you compute the metric there. You act with the, you compute the, use the metric there, and this defines the metric at the tangent space on any point in the group. So fine. So now we have a metric. We have some manifold. We have a Lie group manifold. And well, we all know how to compute geodesics on manifolds. And there's a well-established formalism for doing this. So there's something called the Euler-Arnold equation, misspelled here, which takes this metric and uses the Levi, this sort of, well, you can put any metric, but anyway, we will use this metric and use the Levi-Civita torsionless connection. And Euler and Arnold taught us how to rewrite the geodesic equation in this form. So V here are tangents to the path, F's here are structure constants, V are tangents again to the trajectory, and well, G is the metric. So this is the equation we have to solve, and you can solve this in terms of you find the group elements in the geodesic trajectory in terms of a path ordered exponential. And we have boundary conditions that you start at identity and you finish at e to the minus iht. And well, there are many such paths you could imagine. And the complexity of the target unitary is supposed to be the minimum over all geodesics of the standard path lengths, so Gij, Vi, Vj, where Vi and Vj are tangents to the path. So I hope you will not be following all the details of how I pick the metric, etc. But I hope all the formula looks sufficiently familiar that this, we're just doing standard GR, right? We have a metric, we chose the metric in some clever way, inspired by the computational complexity people, and we're just calculating the geodesic equation in completely conventional ways. And again, this is all intended to demystify the complexity. We're just doing standard geometry of Lie groups, right? And we will get an interesting result. That's supposed to be the theme of this talk. Okay, so let me go to the next page. So in particular, just to show you to do it practically, if you do this with SU2, so that's like SYK with two fermions, here are three generators, gamma 1, gamma 2, and I gamma 1, gamma 2. Let me suppose that the T3 is a hard direction, and let me suppose, and in this basis, the Cartan-Killing form is the delta function, delta ij. So my metric becomes a delta function plus mu in the hard direction. Now let me suppose that I can write down the geodesic equation, right? The Euler-Arnold equation. It's this thing here. We don't have to follow the details. It is what it is. You have to solve it, solve that too, and then you can work out what the length of the geodesic is and find its complexity as the length. Okay, so I'm just trying to emphasize here with this slide, we don't have to follow the details. In any case, we're interested in large M, not SU2, but you can just write these things down and solve them. Okay, so you find some answer here. So in particular, if you look at the SU2 case, you find something interesting. If you look at this, if you measure the complexity as the geodesic length, it increases linearly in this way initially, and then decreases, and then increases, and then decreases. And that is because, and very quickly, it decreases again. So this is a case where the complexity is not increasing linearly for an exponentially long time, okay? And indeed, we didn't expect it to. This is not a chaotic theory or anything like that. But in practical terms, this is happening because initially, let's say the identity, and let's suppose you've got the time evolution going this way. Well, from the identity to that time evolution operator, there's this trajectory going like this. And at some point, a different trajectory takes over and becomes the shortest path. And so because a different trajectory takes over and becomes the shortest path, it goes up. And then as this again nears identity near the origin, the shortest path is the short distance from the origin and goes up and down. Okay, so this is the kind of thing you'd expect in an integrable theory, that the complexity goes up and down, does that kind of thing, right? So in particular, one interesting fact that's worth mentioning here is, you know how in the SYK model, you're supposed to take many choices of couplings and average over them, and it's a disordered system. If you do that here, if you average over them, these sort of little mountains, vary in shape. And the result is if you average them, you'll get a ramp in the complexity and then a plateau. So in this case, the plateau that people keep talking about in SYK-like models comes precisely from the disorder average, producing this kind of averaging out in the complexity that then produces a plateau. But notice it does not rise linearly for an exponentially long time, as we were expecting for chaotic theories. So, so far so good. Any questions? Okay, I'll keep going. So now comes the interesting part. So we need to do this again for general M. Now, in view of the time, I'm not going to go through the sort of technical details of exactly how you solve the problem. So there's some trickery involved in setting up your basis of generating the right way and understanding the math of that. Then when you work out the Euler-Arnold equation, there are, in general, some interesting simplifications whereby the equation for the local, for the motion, the local directions involve some matrix which only involves the non-local velocities, and the equation for the non-local velocities only involves the matrix which involves the local velocities. So there's some interesting simplifications which actually allow us to make progress. We don't have to go into that. This is just there here for talks where there's more time to be had, to show you that it's practical. You can just sit down and just do this. And at the end of the day, what you find is there is always a solution where you start by aiming the trajectory along some direction V alpha in an easy direction. And this will just keep going in that easy direction. So you get U of S is equal to e to the I V alpha T alpha S. And this particular trajectory, which aims directly in an easy direction towards the e to the I HT, will have its complexity growing linearly in time. If you measure the geodesic length for it, the geodesic length will grow as a function of time because the operator e to the IHT is moving away as time, and the complexity, the geodesic length, goes as time times something involving the coefficients of the operators that appear in the Hamiltonian. So this is a linearly growing complexity for some amount of time. Two comments. You might say, wait a minute. How can it be that suppose the Hamiltonian was complex or complicated. How could it be that by flowing in the easy directions, you could ever reach this complex thing that you made by applying an e to the minus iht if the Hamiltonian were complex, for example? I think the answer is, of course, by applying enough local operators, you can always make a non-local one, right? Or as non-local as you want. So you can compose simple operations to do something complex, but it may just take you longer. Okay, so you can always aim your trajectory only in simple directions and still reach wherever you want to reach at the end of the day. So that's an interesting point. But really the question for us to see is, so we know that at least initially you will have some geodesic that shows this linear growth in complexity with time. But then you want to know how long does this linear growth persist? And under what circumstances does this remain the shortest geodesic? Hugo, am I within 3 minutes of my conclusion? Is that what that's supposed to be?
Yes, that sounds good.
Okay, naturally I have much more than 3 minutes to say. So I'm going to try to summarize what I have to say in 5 minutes of it, if you don't mind. And then we'll have a little time for discussion. Okay.
Sounds good.
So we've just established this linear growth in the complexity. So what possible obstructions could there be to this linear growth, right? How can it stop being the minimizing one? There are two possibilities. You can have geodesic loops, basically global obstructions. You go this way, and somehow from some other kooky direction comes another geodesic, it hits it and stops the minimizing. So in fact, showing the absence of global obstructions of this kind is in general a computationally hard problem, right? For specific Hamiltonians and cases, it may not be as hard, but in general, it's a computationally hard problem. And we will not address this point here. But I hope to convince you that a different kind of obstruction is actually interesting. So this is called a conjugate point, right? So suppose you have a geodesic. Here's the linear geodesic we were talking about earlier. It's possible in some cases to deform the geodesic a little bit like this. And if you do that, this geodesic sort of bounces off the wall and comes back in and hits the original trajectory at some point. Now, by deforming the kink you have a little bit here, you can show that if there is a conjugate point, you will get a shorter path through this other way. So if this happens, the linear geodesic, right, the linearly growing complexity geodesic will no longer be the minimizing one, and so the linear growth of complexity will halt. So again, there's no time for this in this talk, but you can show that this is a non-empty problem, right? It is actively an issue that you can have these kinds of conjugate points that mess up the linear growth of the complexity. So it's interesting to ask what properties a theory should have to avoid such conjugate points. And we are going to show that the absence of conjugate points, if you want to eliminate them, is related to interesting problems in physics, including the theories of chaos. So this ECH criterion that we talked about earlier, which is related to the spectrum and the structure of the eigenstates and stuff like that, stuff we're familiar with in physics, unlike complexity, which we're not so familiar with. So avoiding the conjugate points and therefore allowing linear growth of complexity is related to all of these sort of standard concepts in physics, like the spectrum and the as I said, and the structure of the eigenstates and so on. Okay, so how does this work? So the way in which you find conjugate points is you say, suppose you have the unperturbed linear geodesic, that's like this. So the geodesic just travels along the direction of the Hamiltonian. That's the one that has linear growth of complexity. So you perturb it a little bit, you add to it a little bit, and you ask, suppose I shoot the geodesic off in a slightly different direction, right? How does it behave? And does it come back and hit the original trajectory? You want it to come back and hit the original trajectory. And so there's a first order perturbation of the Euler-Arnold equation, of the geodesic equation, called the Jacobi equation, which has some form. So this is just all mechanical algebra. You plug in the perturbation, you grind through, you write out the perturbation theory, and so on. And we don't need to go into the details. The equation's again here to convince you that you can just do this calculation. So suppose you do this, then it gets complicated. All of this is just camouflage to let you know that we actually did some work. So what you need is this situation where you aim the trajectory in a slightly different direction, and then it comes back and hits a point of the original trajectory, right? So you can think about that in the following way. I can think about a super operator that maps the initial perturbation over to a point that's on this, over to a later time. And if that super operator has a zero mode, that's what it means for it to map an initial perturbation back onto the original trajectory, you will find that there is a conjugate point. So I have not explained that in detail. That's all of this stuff going on here because there isn't time for that. But you can see the details in our paper. Okay, so what we're really interested in is what is the conditions for this to happen. So here's what I will tell you. So there are two cases to consider. One is where all the directions are easy. This gives us an intuition for what's going on. And if you consider the case that all the directions are easy, there is no hard directions, right? You haven't declared any directions hard. You do some work and you find out that the critical time at which there will be a conjugate point, right? There will be some other trajectory that will come and stick in, will occur at a time 2 pi over delta max, where delta max is the gap between the highest and the lowest energy in the band of energies that you're considering that are relevant to the dynamics, right? And so in the SYK model, the maximum energy is of order n, right? So you see that if all the directions of motion on the SUN manifold are considered easy directions, you will find that the conjugate points will occur very quickly, namely at time of order 1 over n, where n is the large n of the SYK. Now, if you instead consider a situation like the one we're interested in, where there are some easy directions and some hard directions, right? There are some k local directions that are easy and some of the rest of the directions are hard, and you agree that the theory satisfies the ECH criterion. So there's this ECH criterion for this ratio of matrix elements is suppressed exponentially in the square, in twice the entropy. Right? So suppose you assume that. Then you can do a little bit of work and you can show that up to terms corrected exponentially in exponentially suppressed S, the conjugate point happens at a moment when, again, I'm skipping details, right? This is the same, that calculation, right? Occurs at a time of this order. Again, there's a 2 pi over the gap between the maximum and the minimum energies times 1 plus e to the epsilon s, where e to the epsilon s is the entropy and epsilon is some coefficient that you can put in there. So in other words, if the theory satisfies this ECH criterion,
Is he out of chat?
Yeah, I think Vijay froze for all of us, right? Let's see when he comes back.
Yeah, it's always the fear that it's just for you, so then you wait a little longer.
Unfortunately, Vijay had the McDonald's internet, right? So that could be. Let's wait.
But apparently, we have like 2 of his collaborators, right, in the audience. So maybe we can harass them with the questions if they.
Yeah, we can. Yeah, we can wait a bit and then.
No, he's back.
Hey, Vijay's back.
Looks like I'm back.
Nice. Okay.
Can I share my screen again? I don't know what happened, but
yes, please.
It looks like the McDonald's probably got unhappy with me briefly.
Maybe they have a 1-hour rule that they disconnect you or something like that.
Yeah, that's probably right, but don't have a thing that checks that you're using the same computer again. So here we are back
Very
again.
good.
Okay, can you see this? Can you see my screen?
Yes.
Okay, great. So the conjugate point is shifted off then to exponential time. So I'd like to say a couple of things. So one is in terms of computational complexity theory, if this is true, this has a bearing on a couple of interesting things. So one is, there is the, consider the following 2 complexity classes. P space is a set of problems that can be solved on a classical computer with space polynomial in the problem size and as much time as it needs. Then there's a quantum computer, a quantum complexity class called BQP/poly, which means bounded error polynomial quantum with polynomial sized hints. So bounded error means you get it right with probability 1 plus epsilon. So you can always amplify that to get it right with whatever accuracy you want. And polynomial sized hints means you have the problem statement and then you have a hint that's polynomial in the problem size. So there's a statement due to Aronson and Susskind that P space is not contained in BQP poly if and only if the complexity of the time evolution operator after an exponential time, c to the n, is larger than any polynomial in n. So there's a statement of this kind. So if that, okay, so the latter statement that the that the complexity grows to become exponential in exponential time will tell you that P space is not in BQP/poly. So we are showing that up to global obstructions, which we're setting aside, if a theory satisfies this ECH criterion, the complexity grows linearly for exponential time. And so after an exponential time, the complexity is exponentially large. So in other words, this would say, if true, that P space is not indeed in BQP/poly. So there's a consequence in that way. I'm going to skip the second example and instead go to the last point, which I was about to write this slide when the power went off in my house, and I was trying to figure out how to do all of this. Okay, great. So I'll just say a word about something called Hamiltonian speedups. So one interesting thing to consider if you're building a quantum computer is whether you can build a quantum computer to do to simulate a physical system faster than the physical system. And is there a way of doing the whole system faster? That would mean you construct a different, you make a different Hamiltonian, and effectively you go off in a slightly different direction on SUN, but you come back to the same point, and you somehow do it faster. So our results would suggest that you can't do this, and that in fact Hamiltonian speedups of that kind are not possible in theories that satisfy ECH. Great. So let me stop sharing my screen.
So let's thank Vijay. Thank you very much. So if people want to ask questions, or as I said, maybe send something on the group chat so I can ask Vijay. We can do at least a 5 to 10 minutes discussion session.
So Vijay, I have a quick question. So if I think about this argument in the context of conformal field theories, well, we applied the stress tensor for a while, and actually these applications of the stress tensor seems to be like the optimal trajectory for constructing the unitary operator. But at some point, something goes wrong. So do you understand like what happens in terms of the algebra of operators in a conformal field theory?
So sorry, I missed a couple of things you said. So could you say it again? I'm so sorry.
Oh, sorry. What I mean is that suppose that we do conformal field theory. So in conformal field theory, we generate the Hamiltonian with insertions of the stress tensor, right?
Yes.
And the optimal circuit that governs time evolution is going to be basically time evolution itself, right? This is what you said, up to some point. And at some point, something goes wrong, or like goes differently. And my question is like, do you understand what happens at this point in terms of operators in your CFT?
So I don't. We can ask Onkar and Arjun also. Basically, what you're asking is that when you get to that point, there's some other trajectory that could be a conjugate. You could get a conjugate point by moving in some other way, and that has to have some consequence of which what operators are being used to get there, and what operators you can generate.
Exactly.
So I don't think we have an understanding of that. We didn't specifically study that question, but let me ask Arjun and Onkar if they've thought about that since then.
Well, I haven't thought about it, so for a chaotic CFT, I don't know the answer. But for a free CFT, I think we understand the answer. So for a free CFT, what happens is that if you look at the trajectory e to the IHT, then you can show pretty generally that anytime your theory has a simple operator, which is sort of has a which is an eigen. So to be precise, it's an eigenvector of the adjoint action of the Hamiltonian, which is just a fancy way of saying that it's like a creation and annihilation operator. Anytime you have a simple notion of a simple operator which acts like a creation and annihilation operator, then you're guaranteed to have run into a conjugate point at order 1 time. So in that context, I think you can. So I think what I'm saying is that by sort of deforming the trajectory, the initial direction of the trajectory by these simple operators, these particular ones, the creation and annihilation operators in the theory, you can lower the complexity after an order 1 amount of time. But this is only a statement about free theories. Potentially also this works for weakly interacting theories also, that is, although we are currently investigating that. But I don't know about the more general situation.
Great, thanks very much for that comment. Indeed, there's some work we're trying to do for weakly interacting theories and for integrable theories. You might think that integrable theories also you can get some control over in such manner. And so, but in general, I think we don't yet have a grip. I see two questions in the chat. May I address them?
Yes, please. So do you want me to read just so?
No, I can read them too.
You can read.
So
Perfect.
So the first one is by Luca Tagliacozzo, and he says, what is the relationship with the complexity of diagonalizing the Hamiltonian that generates the evolution? Okay, so that's something also that I haven't thought about. I mean, that's equivalent to finding the set of eigenstates of the Hamiltonian, and is related to the question also that Rob asked at the beginning.
Yeah, just maybe, yes, maybe to add something, because once you have diagonalized the Hamiltonian, the evolution is free, right? So somehow
the evolution is right, but
so in the sense that you just add local phases, and so in an operatorial sense, you don't need to add anything else. So to me, it's a bit strange that the complexity grows in time. So maybe it means that actually, in order to diagonalize the Hamiltonian, you need exponentially large, an exponential number of gates from the beginning, right? Something like that.
That's probably the case. Probably somebody in this audience would know that better than me. But I'm thinking for a moment about the question of, it's certainly true that if you write your state in the basis of energy eigenstates, clearly you just add phases to everything. But then you might say, I think you're saying, then why is the evolution in any sense complex, right? But I think in some way, okay, so that's not sort of a local change, right? So of course the
no, indeed. So the question is, how complex is this change? Yeah. Yes, okay. And yeah, possibly if it keeps growing in time and it saturates only to the exponential thing, it really means that you cannot diagonalize it simply.
Yeah. Right? So conservation of hardness somehow must somehow imply that is the case. This is the kind of thing certainly people have thought about in I'm sure theories of computational complexity. I see various people nodding. So if someone else has a comment about how hard it is to diagonalize the Hamiltonian in general, that'd be great.
Yeah, isn't this, the quantum information friends can probably say something more meaningful than me, but isn't like the local Hamiltonian problem in QMA in general? Like, I think that would imply that this is a hard operator, but again, my quantum info friends can, yes, I think Scott has said that it's QMA
local Hamiltonian is QMA complete.
Yeah, okay.
Okay, and Norm Margulis says, if you, let me go down the list, okay? So Abhinav Deshpande says, if you're in your eigenstate complexity hypothesis, is it necessary for the gamma mn to be random numbers? Perhaps you only need them to be upper bounded by some order 1 constant. So at least in the way we formulated it, you only needed to be upper bounded by some order 1 constant. But actually, we've been continuing to think about whether whether we've stated the condition that we've tried to state sufficiently in a sufficiently refined manner, or further refinement is necessary, or could be stated more carefully. So we don't have, but at least as I stated it and as I used it, we needed it to be upper bounded by some order 1 constant. Yeah.
Thank you.
So Arijit Pal says, could you say a bit about the saddle point of the trajectory, classical limit, and its relationship to the complexity of U of t? So the trajectory here is a classical trajectory, in the sense that the equation you're solving is the geodesic motion on the group manifold. So it isn't a sum over trajectories. Does that clarify, Arijit? I don't see a response. Oh, yes, he said
thanks. Yes.
Yeah, wonderful. Okay, from Norm. If U of t describes a classical computation traversing a sequence of distinct states, assume the geodesic is obviously linear in time. If it's classical, traversing a sequence of distinct states, assume the geodesic is obviously linear in time. Actually, is that even clear to me? Actually, the reason that's not completely clear to me is what if the classical trajectory computation was, the classical evolution was itself chaotic? Then, actually, that's not clear to me. Ankar, Arjun, do you have any thought on that? Maybe not.
I'm not sure I completely understand the question.
If the computation is classical, right? So here we're talking about a quantum. The first question is how you make the computation classical. I fully understand that in our language. But then suppose you have a classical computation just going through some sequence of states. The statement here seems to be that geodesic is obviously linear in time. That's not obvious to me because, you know, I would have thought that there could be very complicated trajectories, and then if you want to just
by a classical computation, I just meant, you know, some sequence of gate operations which happen to be permutations.
Oh, okay.
So the quantum computer is only doing a classical computation.
Okay.
And it's a reversible computation, so it goes through a sequence of mutually orthogonal states. And the shortest path, I would think, has to be in linear in time, right? With the number of steps. I'm just trying to understand, this is that's sort of a trivial question. I'm just trying to understand the classical case.
Yeah, so in that case, a simple classical computation would involve a permutation involving, you know, a cycle structure involving less than k elements or something. Right?
Yeah,
so,
well,
that's what would be a simple permutation, simple classical operation versus a complex classical operation that would permute more things at the same time, or the cycle structure more complicated.
Sure, but
okay.
Assuming, you know, at all a complicated system, it's going to have a long cycle, and for the course of your computation, it's not going to have cycled yet. In fact, you know, if you're doing a computation, all the steps from the beginning to the end will be mutual, will be distinct, because you know, otherwise you've cycled already.
Right. So you're saying that this will last for a very long time, just basically because the permutations won't come back to themselves for a long time.
Well, and whether it does or not, if you're talking about a particular computation, which hasn't returned to the initial state yet, then it's reversible. You know, they're all distinct. So it's gone through a sequence of mutually orthogonal states. Sorry, I thought this was a trivial question. I'm not trying to.
Yeah, yeah, no, I understand. But that's a great. Well, it's an interesting question, at least to me. But, let me tell you what I'm confused about. So suppose I do a, and you know, anybody else who immediately wants to chip in, please do so. But what I'm confused about is, suppose I indeed do some series of permutations, and then we want to say that we want to compute the length of the shortest path along the part of the group which involves permutations by less than k elements. And the argument that one would like to make here is that this is going to persist for a very long time without any conjugate point, because there is no way of producing that permutation through any other means. Right? Because after a sequence of steps, what's effectively happened is you have some permutation of the bits. That's what you've done. Right? There's no other way of doing it, you say.
Yeah.
Using,
if I may.
Yeah, so maybe let me just do a very friendly cutoff to the nice discussions we've been having. So let me propose for everyone who wants to take a 5 minutes break to do it now, and then we start Nicole's talk in 5 minutes. And let me just very briefly say, then Vijay, correct me if I'm mistaken, but probably today you might not be able to join us for the discussion after Nicole's talk because of power out problems, but maybe you will, right? It's TBD scenario.
So in the, I am going to now drive home and see if power is restored.
Yeah, that sounds good. But yeah,
but thanks
just
very
in
much
case.
for having
Yeah,
me.
thank you very much. Yeah, and please, if
A lot
you
of fun.
want to keep talking for these 5 minutes, feel free. And in 5 minutes, we resume with Nicole's talk. Okay. Thank you very much.
Bye. Bye.
So I just want to clarify the question that Norm was asking. By classical computation, would you say that like you're transitioning between a series of states which have very small overlap with each other?
We have no overlap. They're mutually orthogonal. A classical computation goes through a sequence of mutually orthogonal states.
Right.
I'm thinking of maybe a synchronous computation, classical synchronous.
Right. And so the interesting point there is that there seems to be, for that particular trajectory, there seems to be no way of having a conjugate point. I think that's what you're saying.
I guess, yeah.
Oh, cool. Okay.
I'm just trying to think of this as a generalization of the classical case.
Right. So we didn't say anything here about permutations per se, but perhaps, so one of the challenges for us has been trying to say anything whatsoever about the global properties of these trajectories. So besides the conjugate points, there's the issue of, are there global obstructions? So I wonder if, at least in the vicinity of such trajectories, right, the permutation, the vicinity of nearly classical computations or something, maybe there's a way of leveraging what you said to gain some control.
Okay, cool.
Okay, so I don't have a more intelligent remark than that. I'm afraid.
Sorry, I thought I was just asking sort of a stupid question because I don't understand about these these complicated things. All right.
Okay, interesting. Okay, thanks. There's a bunch of comments by a bunch of people.
Again, if I may ask Norm, is your question, inspired by the theorem of after your name, right? Which says that if you have a system, then which transitions between its orthogonal states, right? So you can define a sense of time in using that.
Well, it is in a sense because you can actually prove that if you have an evolution going through a sequence of orthogonal states, the shortest evolution has the orthogonal states equally spaced in time. And so it would be going at a constant rate.
Right. Yeah, exactly. So then in that sense, you're saying that it's a trivial statement, because of a consequence of the theorem.
So Michael Walter, Michael, you should probably just say this yourself, writes that if you take the complexity of a permutation to be the number of swaps you need to write it, then p squared need not be more complex than p.
Yeah, I think it's a bit different. I mean, like I think the model that you considered where you're trying to decompose a unitary into small building blocks seems a bit different from the question like how many orthogonal states can we run through. So I don't. So I think the question that you considered seems more in the classical analog. I think would be more you have a big permutation and you're trying to write it, as you were saying before, say a product of local permutations, which for example could be say transpositions or something like this. I think then you should have similar effects, right? That you can have shortcuts and so on.
Right. Okay, I'm going to sign off now and try to log in again after I get home. Thanks again for inviting me.